So in the last class, we have learned how to evaluate especially the dynamic earth pressures for stability analysis of a retaining wall. Right? So whenever we have a cut slope or we have certain slope which needs and protection, all right, so we adhere to retaining walls, and when there is an earthquake, we observed that the earthquake dynamic forces, they act on the retaining wall and they try to destabilize the retaining wall. So to and design the wall properly so that it does not collapse under the dynamic load. So we have to assess what are the different forces which may come into the dynamic, into the retaining wall, and we have to design the retaining wall in that manner so that it remains stable under earthquake seismic forces. Now, apart from that, now we have to analyze. So there are also various cases where we have to analyze the slope stability of the slopes. All right. So slopes. When I say slopes, all right. So we may divide them into obviously two parts. All right. One is definitely natural. All right. We are surrounded with hills. All right, mountains. All right, so those are natural slopes. Then obviously man-made. Right? Now man-made means it may be even a cut slope also. So in a hill slope, so we make a cut, right? Even that also we can consider man-made. But apart from that, so one of the most critical, subject, one of the most, discussed subject as far as stability of slopes or the analysis, stability analysis of slopes is concerned, is basically of the embankment type. Right? So where do we encounter embankments? In various cases. So suppose, let us start from the simple case of the roads. So roads in Assam, right, or in many of the cases, in fact in India or even abroad also, so many roads are built on embankments. So on top of the embankment we make an embankment, and on top of that there is the road, right? So to keep the road away from maybe flood, right? So there is flooding, so to keep the road on top of the flood, right, so that there is unabated or unobstructed flow of traffic, so we construct embankments. Railway lines are obviously mostly in Assam, right, and in various parts of India as well. They are constructed on embankments, all right, and in fact we also on top of embankments we give the ballast, right, so to aid in, I mean, the drainage outside, or to keep the railway tracks uh, dry at all conditions. Then apart from that, it also helps to transmit the forces, right, to the environment, or right, it distribute the forces or distribute the stresses. So we observe that slopes maybe are mostly natural and also man-made, all right. So, and the man-made slopes are mostly related to the embankment types, all right. And obviously natural slopes, if we consider, they are made up of various types of material. In various types of material means, I mean the soil, all right, and it may be rock. All right. So recently we observed when there was an earthquake. So in Bhairav, all right. So there was a huge landslide. All right. So we need to assess we need to be able to assess what are the different types of seismic forces which may come across when there is an earthquake. So, and we have to analyze so whether the slopes will remain stable under that condition or not. One of the things that we are going to study is that this stability analysis of slopes which have been developed, the entire subject matter which has been developed so far is actually based on the stability of embankment types. All right. So it was started as a subject matter for stability analysis of slopes of embankment, and then it was ultimately means used for the analysis of natural slopes as well. Of course, some changes were made in that. Some changes were made, and so when I say slope stability, so obviously we are going to see one classic case of embankment slope stability analysis, which is widely studied. But before that, just want to give an idea of the earthquake-induced landslide, right? And what havoc it can cause, right? So landslides, it can occur. Landslides. When we say the term landslide, it is mostly associated with the natural slopes, all right? And obviously, the damage what it causes, it may be insignificant. If a landslide occurs in a faraway land, we will see, all right, in northeast India, there are numerous landslides, right? We will see that today itself. And a landslide occurring in a faraway land where there is no people living, all right? So the damage is, in fact, there is no road also, all right? So in that case, the damage is insignificant. But sometimes what happens, those kind of landslides, they build, they give rise to natural dams, right? They give rise to natural dams. Now, natural dams, so it is made up of the landslide debris. You can just imagine it is made up of the landslide debris. So it is very soft, loose material, right? So what happens for a momentary time, for some time, suppose maybe a month or 2 months or 3 months. So what happens? So we have a river, so it is flowing like this, and suddenly there is a landslide and there is a dam. So there is a rise in the water table there. Alright. So as soon as the water table rises, alright, so the dam is now under stress, and it is already a natural dam. Alright, it is just the debris being dropped down there. Alright. So then it starts eroding. Alright, and there is overflow, and then what happens, that this dam collapses. Now collapse of such natural dams, all right, is a very catastrophic matter, and it causes flooding to the downstream areas and huge loss of life, and there is destruction everywhere. All right, it is a disaster. So that also we need to see. Of course, we will not discuss that in here. I am just giving you an idea of what slope failure may lead to. All right. So, of course, different types of landslides we will discuss later, as we will see. So as we start, so here is one of the earthquake-induced landslides. So it occurred in El Salvador, right? So Las Colinas landslide, and it claimed more than 500 people. All right, so you can see these are the houses, small houses, all right, and it washed away everything. All right, so huge landslide. So this is the landslide body, and from here the mass got dislodged and it flowed down, alright, and it caused an havoc at the bottom slope. So it occurred in January 13, 2001, alright. So here is an earthquake triggered by Kumamoto earthquake, right? So in fact, not only this, so this is the biggest landslide. Here you can see here also. So there are several entire this embankment or the slope. All right. So it got dislodged. All right. And obviously this landslide. So this landslide you can see. All right. So it flowed down. Right, and it washed away whatever houses were here, right, and the road, everything, right. It is Japan. So this is another landslide triggered by the same earthquake, all right. So this is another landslide, so it obstructed the road, obviously, all right. So you can see this is the escarpment here, right. So maybe this went out here like this. So Northridge earthquake in January 1994, it was magnitude of 6.7. And it triggered 11,000, over 11,000 landslides in the San Fernando Valley. Alright, San Fernando Valley. So, and you can see that it is mostly rocky slopes, and you can see the rocks being dislodged. Alright, the rocks being dislodged. Alright, so from here it is dislodged in this manner, and the rocky, this basal layer is exposed now. Alright, the base rock is exposed. And obviously if you see, if you look into Sikkim, all right, so Sikkim in September 2011, so there was a earthquake of magnitude 6.9, and it gave rise to numerous landslide. Now obviously this is a fresh landslide which occurred there. Now here you see it is, these are old landslides. Alright, so this region itself is not very stable. Alright, so September 2011 it gave rise to this particular landslide. Alright, and here we have observed, here we can observe that it is already, there has been landslide previously also. Right? So there are various types of landslides. So first of all, there is the rock. If we consider the material, one is the soil and the other is the rock. Alright, so rock, when we consider rock, so there is toppling of rock. Alright, so we say rock fall. Alright, then rock slides also. So there are rock slides also. Alright, and obviously avalanche, when it is almost, it is fissured rocks and the rocks they roll over and there is a huge landslide. Alright, similarly we have translational slides when the soil is mostly cohesionless, or it is like a granular soil, so we have the translational slides. Rotational slides or slump is when we have a cohesive component in the soil, all right. And obviously when it is mixed with rock, soil and water and everything, and it flows out at very high velocity, we have the flow type of slide, debris flow, right. So there are various types of landslides which may occur, and we have to analyze that. Now these are, whatever we have discussed, are natural slope, right. So one of a classic case of man-made slope is the failure of the San Fernando Dam. Right, so it is a dam. It is a dam which was, which failed. All right, so it was triggered by an earthquake of magnitude 6.6 on February 9, 1971. All right, so this dam, it failed during the earthquake. And There has been numerous case studies of this particular failure, right? So you can find out when you type San Fernando Dam failure. In fact, there is one particular software suite which is Slope W, all right? So Slope W, or actually it is yeah, Slope W, all right? So uh, I mean, this case, particular case, has been addressed as a, I mean, verifying case, right? So there you can find out also. So what happened here was, so a soil beneath the dam, a soil region beneath the dam, it got liquefied. So this region inside the dam, it got liquefied. All right. And after the dam failed, so various researchers, they tried to map the failure. All right, so they tried to map the different particles, and then they, I mean, reorganized the things. All right, and they mapped at which parts were the slips or the failures occurring. All right, and they mapped the failure of the slope. All right, and it was extensively studied, this particular dam failure, and of course many of the things that further got developed, all right, only after this particular case study. So this is a classic case study. You can go through that. So so when we say earthquake-induced landslides, all right, so they are basically they can be divided into three this points, or three parts. All right. So one is disrupted slides. All right. So, or we can call it the quick failure type of slides, which involves the rock falls or the rock slides. All right. So in this case, what happens? The materials, they are sheared and broken. All right, and they are disturbed into a broken and fissured, mass. All right, and suddenly when there is a jerking, when there is a, dynamic seismic force, so it suddenly fails, and it produces, it fails in an extremely rapid movement. All right, and there is devastating damage. Of course, damage and things will be, if there is vulnerable factor there. That is, of course, a different case. But thing is that, like in the Bhairavkund, this failure, all right. So Bhairakundo failure. So there, what happened? Suddenly, the rock, fissured rocks, it failed. All right. So there is the disrupted slides. Then there are coherent slides. So where there is soil slumps. So there is soil type, and it slumps and it fails. All right, and it is mainly in the moderate kind of slopes. All right, and it is somewhat of lower velocities. And then there are lateral spreads. So lateral spreads actually is when there is very gradual slope, very, low, range of slopes. All right, and they involve generally the liquefiable soils. All right, so when there is a liquefiable soil, so suppose it is gentle slope, so and the soil liquefies, so the soil flows. All right, so we have the lateral spread. Of course, we will analyze those also. When we will analyze the displacement analysis of slopes, we will analyze them. Now, as I have told that the slopes analysis of slope stability, it was developed mainly to analyze embankment slopes. All right, so and then it got utilized in analyzing the slope failures in the natural slopes. So what is done is, again, just as we have learned in the Coulomb's wedge method, so we apply the limit equilibrium method. So that was the first method which, that was the method which was developed for analyzing the stability of the slope, analyzing the stability of the slopes. So limit equilibrium method. So what is this limit equilibrium? So thing is that we have a destabilizing force, and we have a stabilizing force. So if we consider this one, so this particular soil mass has a weight, all right? So it has a normal component and it has a tangential component. So the normal component will give rise to friction here, all right? So the friction is basically the stabilizing force. There is none other than that. And obviously the tangential component of the weight itself, all right? So due to the gravitational or inertial, as I would say, all right? So gravitational force or the inertial forces. So this mass tends to slide out, all right? So in limit equilibrium, what we say is we find out what are the different forces, and we assume that the soil is about to fail or about to slide out across a failure plane. So the first step is, again, we assume the failure slip surface. Then we, after assuming this slip surface, we find out what is the normal component on the slip surface, what is the tangential component on the slip surface. Once we know the normal component, we multiply, or we find out what is the friction available in that slip surface, all right? What is the friction available in the slip surface? And that shearing resistance, all right, that friction is basically the shearing resistance of the soil. All right. So then we define a factor of safety. So when we define the factor of safety, we say, so factor of safety is this available shearing resistance or shear strength. So that is the failure shear resistance, or the shear resistance at which the soil will move out. All right. So that is the available shear strength of the soil. So which we measure from various laboratory tests and other things, and obviously the applied shear stress. Now this is factor of safety for the force. So similarly, we also have the factor of safety for the moment. So factor of safety for the moment also we have. So in that case, it will be the available stabilizing moment, all right, or we have the available stabilizing moment, all right? So available stabilizing moment by the destabilizing moment. So we will see, all right, so how we can easily understand the things, we will see that. So we have two equilibriums. One is the force equilibrium and one is the moment equilibrium. So as long as the shear strength or the shearing resistance of the soil is more than the applied shear stress, the slope is stable. When the applied shear stress exceeds the shear strength, then there is failure, right? So here, so we have, so apart from that, we have various modes of failure. So of course, one is the translational. All right. So this is mostly the failure mode of granular soils. All right. So granular soils or frictional soil. So we have the phi value. All right. And C is cohesion is, approximately 0. It tends to 0. All right. And so this is translational motion. So where the wedge or the failure wedge, it fails in translation. It simply slides out straight. All right. Linear movement. Again, there is a rotational movement, rotational slump, which we say. So there is a point of rotation here. So this particular type of failure is mostly characteristics of cohesive soil. So this is the characteristics of cohesive soils. Now, definitely in nature, soils are neither absolutely granular, we can say, or absolutely cohesive. So it is somewhat mixture of the two. So we have the C5 soils, all right. So we will have various, and we will also have various geometrical, discontinuities in the slopes, all right. So there will be various layers in the slopes. So there will be various layers, all right. So that will give rise to this kind of discontinuous slip surfaces, or slip surfaces with different geometry. So here this soil, this particular soil is mostly cohesive. Alright, and here at the bottom, alright, we have a soil which is very, it is granular. It is, its behavior is like granular, and is very, weak soil. All right, and the friction is very less. So we can say that here there is a curved, here there is a linear, again there is a curve. So it feels about. So maybe this soil also, maybe it, it is like a liquefied soil also. All right, so the failure may be of this sort. So we have various modes of failure. So mostly two extremes are, one is translational and one is rotational, and we have things in between that. All right. Now to assess that, as we have analyzed, to assess the stability of the slopes. So the method which has been so far mostly used is the limit equilibrium method. All right. So of the limit equilibrium method, this is the wedge method. All right, and this is the friction circle method, you can see. All right, or a circular failure mode. All right. Then of course, then various methods. The most prevalent of the limit equilibrium method is the method of wedges. This method of slices. All right. So method of slices was developed. So we will, as we go on, we will study all of this. So method of slices was developed. So what we do is we divide the entire slope into slices, and each of the slice we analyze the forces, all right, and then we sum the forces, in the x direction, sum the forces in the y direction, and sum the moments in the z direction. Alright, so in the z direction we sum the moments about maybe this axis here. Right, so this is the failure axis. So about the z axis we sum the moments. Alright, so whatever is the destabilizing moments we sum, whatever is the stabilizing moments we sum. So that is a factor of safety against moments. Then for the similarly for the forces also we do the same thing. So we can see that when there is a failure, all right, when there is a failure, so we have different points in the field, I mean in the slip surfaces, and there are they are at different stress conditions. All right, so when so the first failure or the maximum shearing, they occur at the point of maximum shear. All right, so A point will shear, and then it will lead to the shearing of the B point, then it will lead to the shearing of the C point. So ultimately here you see, so A point is here. As soon as A point shifts here, A point shifts here, so the B point rises to the top. So that means now the B point, the entire shear resistance of the B points are mobilized. Once that gets used up, all right, then the entire shear resistance of the C points will be mobilized. So in that way we have a failure of the slope. So this kind of progressive failure, as we say, so these are what we can say is progressive failure. All right, and it has been observed mostly in the strain softening. All right, so you see, so it is strain softening. So A point, this is the peak shear resistance. So as soon as there is exceedance of shear applied shear here, so the resistance of the A point shears and the resistance drops to this point here. All right, so this is strain softening behavior. All right, so in fact most of the slopes which fail, they are quite abrupt failure. So it is almost of this sort. So the slopes they remain stable. As soon as it somehow exceeds this peak shear resistance or shear strength of the soil, then there is catastrophic movement, and suddenly the soil so fails. All right. So I mean, what is the takeout from this, and how we need to consider these things? We will again come back when we see what is the basic methodology we adopt for stability analysis of slope. So, for analyzing slope stability, all right, what we use is the limit equilibrium method. So what we do here is, we have, as we have discussed, so we have the weight, so we have the normal component of the weight, and we have the tangential component. So this is the static case. So we have the weight, and we have the normal component of the weight, and we have the tangential component of the weight. So this is the static case. When there is an earthquake, so we do the pseudostatic analysis. So when there is an earthquake, what we do, so this is W, we have W, that is the weight of the wedge, So apart from that, we have an inertial force. We add an inertial force to the soil. So that is K into H, KH into W. Alright, and we may add another inertial force. Alright, so it may be downward or it may be upward. Alright, so that is KV into W. So what we are assuming is that the soil is basically a rigid mass. Alright, and there is no movement whatsoever within this particular wedge. Alright, so inter particle movement within this wedge is not there. So this is a solid wedge, so absolutely solid wedge, and this wedge, it moves as a solid body over this slip surface, So we have the normal force and we have the tangential force. So tangential force is basically the stabilizing force, T. Alright, and whatever force, the summation of force in this downward direction, that is the destabilizing force. So factor of safety is basically T divided by this destabilizing force. Alright, so I can say this to be T T. Alright, so T. So that is the factor of safety against translation. Alright. Then, so what we have is, so we need to find out what is the area of this wedge. Alright, so we have to find out what is the area of the wedge. Okay, so once we find out what is the area of the wedge, we need to find out the weight of the wedge. So gamma into volume of the wedge. So if we consider unit length in this direction, so unit length in this direction, again we will have so unit length is in this direction, that is, so this volume we can replace it by area into unit length. Alright, so gamma into A is basically the W that we are concerned with. Alright, so that is the W. Alright, then if there is cohesion, alright, that also we can take into account. We can assume, actually we are all of the things here we are assuming. Alright, we are assuming that the soil will fail in this particular manner, and if it fails, then what is the factor of safety? Alright, what is the factor of safety? So it is not that the soil will fail in this manner only. Alright, so uh, we have the cohesion and C into this length AB. Alright, so that is the component force from the cohesion. Alright, component force from the cohesion, so that is the stabilizing force. Then again, so here you see, so this is the normal force, this is the normal force N. Alright, so this is the normal component N here. Alright, and this is the normal force or normal reaction to that particular normal force from the wedge. Alright, so this is the reaction here, and the coefficient of friction is tan of phi. Alright, so phi is the angle of internal friction. So coefficient of friction is tan of phi, so T is equal to mu n, alright, plus C into this length. Alright, so this cohesion component, and this is the wedge normal component of the weight of the wedge, all right, and into 10 into 5. So this is the total shear resistance, right, or the maximum shear resistance or the shear strength. So maximum shear resistance or the shear strength. Then similarly we have the tangential component. Alright, we have the tangential component. So here we can say FB, is plus minus FB, we can say. Alright, and similarly here also this will be plus minus FB. Okay, so we have to find out in which case the factor of safety is the lowest. Alright, we have to change the angle of beta. We will change the angle of beta. So with changing the angle of beta, if I plot, so this is beta and this is factor of safety. So we will have the factor of safety in this manner, right, with increasing beta. So here we have a high factor of safety, then at particular beta we will have the lowest factor of safety. So that is the critical slip surface. So that is the critical slip surface. Now critical slip surface means the slip surface with the lowest factor of safety. It does not necessarily mean that I mean in this case it will mean that the failure is most likely to occur through that particular slip surface. Now in certain cases what it will happen is that the factor of safety may be less than 1 in a range of slip surfaces. So this is factor of safety 1. So in a range of slip surfaces we will have a factor of safety less than 1. Alright, so we can say that that is a failure zone. So that it is likelihood that entire I mean wedge or the entire the slip surfaces, all right. So in there may be a progressive kind of failure. So it may start with the steepest one. So if this is the slope, it may start with the steepest one and then it will retrogress in this manner, all right, and then from here so it will fail up to here, right. So we have, this is the force equilibrium, all right. Similarly we have the moment equilibrium. So here again we have the soil mass. So this is the soil mass. So we have a density, we have an area. So area into density is the weight, and this is the centroid of this area. So the force, we can consider the weight to be concentrated at this point. Similarly we have this wedge over here, alright. So it has a particular density, unit weight into this area will give the weight of this wedge, and this is the centroid of this. So if there is a W acting here, so there will be a if this is the center of rotation, so we have a moment of this W about this in this direction. So this is destabilizing. So this weight will have a moment in this manner, alright. So this is the lever arm and this is the weight. This is the lever arm and this is the weight. So this is in this direction, this is in this direction. So destabilizing, alright. The weight is destabilizing. So similarly what we can do now, C, for if we consider the cohesion, what we can do is we can consider the cohesion to be normal at each point, alright. So we can consider this cohesion to be normal at each point. and the entire C, I mean the resistive moment from the cohesion component, all right, it will be acting along this direction. So this is the lever arm, all right, at each point. So radius is the lever arm, all right. So radius is the lever arm, and at unit length we can consider C to be acting perpendicular to the or tangential to the slip surface, all right, and then we can sum up the cohesive component. So the moment due to the cohesion, so MC we can say, all right, that is the stabilizing moment, all right, and the moment due to the weight of the wedges, so that is the destabilizing moment, and ultimately we will have a factor of safety against rotational stability, all right. So this is the rotational stability. So this is the rotational stability. Now here again we may have the horizontal forces due to the earthquake. Now when we consider horizontal forces, then lever arm will change. So now the lever arm is here. Alright, so the one horizontal force is acting here of the top wedge. So I will change the color. So this is the lever arm now here, alright, and this is the force KH into W. Alright, so this is KH into W and this is W. So we have this lever arm and this force, and similarly we have this lever arm and this is the force. Alright, so we have additional moments, destabilizing moments due to the earthquake condition. Alright, so we are considering it as a pseudostatic analysis. So for the earthquake condition, so we have additional horizontal inertial force acting on the wedges on the soil mass here, and it will be in the horizontal direction. So as we have discussed earlier, as we have discussed here, so I will just clearly mention it. So again, if we consider the weight of the wedge only, so if we consider the weight of the wedge, so the weight of the wedge will act downwards. So this is the lever arm. So this is the center of rotation. So this is the lever arm, and it will act at this point like this, and the moment will be in this direction. Moment will be in this direction. So that is the moment of this weight, the upper top layer. All right. Similarly, we have this weight, so it is acting down. So we have this moment, this lever arm. All right. So it is acting in this again, destabilizing. All right. So it is trying to move the soil mass, rotate the soil mass out of the position here. Now, if we have earthquake, so we consider the pseudostatic analysis. So what we will do, we will just apply a horizontal coefficient of acceleration. So we have a KH into W here. So this is the inertial force due to the earthquake. Similarly, here also we will have an inertial force due to the earthquake. Alright, so what will be the lever arm? So here this is the center of rotation. So this is the lever arm here. So this is the lever arm, and this is the force. And similarly here for this weight, so if we extend it to the point of application here, so this is the inertial force and this is the lever arm. So we can say that there is an additional moment due to the earthquake, and it is quite, it is also affecting the stability of the slope. And if we consider only the cohesive component, so we only that stabilizing component will remain the same as it was. So we have the cohesive component along the slip surface here. Alright, so this will give rise to a stabilizing moment in this direction. Alright, so this will give rise to a stabilizing moment in this direction. Okay, that is from the cohesion of the soil. So this is the rotational stability analysis. Alright, so both of them are limit equilibrium analysis. So this is limit moment equilibrium, and that is limit force equilibrium. Alright, so this is limit force equilibrium, and this is limit moment equilibrium. So to as we have observed, to increase the efficacy of analysis. Alright, so we have it has been the method of slices has been developed to analyze the slope stability. So this is the Swedish circle method. Alright, the Swedish circle method of slope stability analysis, which was the first among the first method introduced by Fellenius in 1936. Alright, so that is the Swedish circle method, and the basic idea is we divide the slope or the failure mass into different slices. Alright, and again, as we have discussed in the earlier cases, we first find out the force equilibrium and the moment equilibrium of this slice. Alright, to include, again, as here the modified, we have modified it for the analysis of pseudostatic case. So here also to include the earthquake forces, so one coefficient of one inertial force is added, alright, in the horizontal direction, and that particular inertial force, alright, so it also induces a destabilizing moment. So along with the destabilizing force, so ultimately we have to find out what is the force equilibrium of this. So summation of force, destabilizing force and stabilizing force. Alright, so whatever we have discussed, the same thing, only thing is that this is now a slice, only a slice of the slope, and here we have considered the entire slope as a wedge, right? So the same thing. So we will stop here today, and tomorrow we will discuss the modified Taylor's method. So that Taylor in 1937 he gave a lot of charts. He solved the solution for slope stability analysis, and he gave charts, and we will see how to make use of the charts to quickly do a slope stability analysis in pseudostatic case. Okay, so we will stop here today, and here